Hello everyone. Let's conclude our discussion on setup timing analysis with multiple clocks. So we came up with a satisfying equation for the setup time which said that the combinational delay should be less than the shortest window, which is 0.5 nanosecond, minus the setup time, which is 10 picosecond in this case, minus the interclock setup uncertainty, which is 100 picosecond in this case. So this is the this becomes the satisfying condition whenever you are doing a setup timing analysis with multiple clocks. So this is a slightly different from what we saw till now, because in the previous case this was not the shortest window, it was the actual time period t, and in this case it is the shortest window. Okay, so by putting these values onto this particular variables, we see that the commercial delay comes up to be 0.5 minus 0.01 minus zero point 0.1, which comes around to be 0.39 nanosecond or 390 picosecond. What does this say? So this says that the path that we had traced in our design, which will be coming to very soon, the path that we have traced, the combinational delay of that particular path should be less than 390 picoseconds or 0.39 nanosecond. Okay, that's what this particular thing says. If it is less than this, if the combinational delay is maintained below this value, or if the setup timing analysis equation is maintaining this, is satisfying this particular equation, which means the circuit will work for any kind of scenarios. It can work for this kind of scenarios, it can work for a scenario where your launch is over here, well, capture is over here, and any kind of scenarios the circuit will work. Okay, that will guarantee us. Okay, second thing, so what we'll do is now the second part of it, will take the real example, will identify the timing paths from the design with multiple clocks. Okay, with that said, we have this section of the circuit where the clock for this particular flip-flop was coming from clock 1 and the flip-flop 2 was receiving clock from clock 2. Similarly, the flip-flop 1, the green color flip-flop 1 was receiving clock from clock 2 and this guy was receiving clock from clock 1. So basically these two are the examples of flip-flops with multiple with multiple clocks, and these two are related clocks. And why do we say so? Because we see a timing path from clock 1 domain. So this we see as a clock 1 domain because the launch flop receives clock 1, and this is the clock 2 domain, and there is a timing path from flip-flop 1 to flip-flop 2. So these two clocks are related, and hence it makes complete sense to do a timing analysis for this kind of flops. Okay, so let's trace those, identify those timing paths. So we have this section, which is the blue colored, from flip-flop 1 to flip-flop 2. So we have this section from flip-flop 1 to flip-flop 2 with all the buffers, which are all the buffers and the combinational cells which are placed in center. And we have this second section which is from flip-flop 1 to flip-flop 2 with this cell. So it's again from flip-flop 1 to flip-flop 2 with this set of cells and buffers. This buffer won't come into picture for now because it's an IO path. It comes from an input port, and it's not an IO path, it's an input to reg path. So you have a signal, or you have a path that comes from the input port, and it ends at the register. So this is an input to register path. So this won't come into picture for now because DIN4 might be clocked with the same clock, for example clock 2, and flip-flop 1 is also clocked by clock 2. So this section of the path from DIN4, the input port DIN4 to flip-flop 1 might come from a similar clock, the timing paths with similar clock. We will not enter into this section. We'll talk about this in a separate static timing analysis about the into reg paths. Let's now focus on the timing paths with multiple clocks. Okay, so these two encircled ones are the timing paths from the design with multiple clocks. Let's try to identify the combinational delay out of it. Okay, so we have removed everything else from here. So now the combinational delay for the blue colored logic, it comes to something like this. You have the flip-flop 1 clock to Q delay. Okay, we have the estimated wire delay between flip-flop 1 and the logic cell 1. We have the delay of this particular cell, which is logic 1. Not logic 1, basically logic cell 1. The estimated wire delay between logic cell 1 and logic cell 2. Okay, then estimated or not, no, the real delays of the logic cell 2, the estimated wire delay between 2 and the buffer. Okay, then we have this buffer delay, and finally we have this estimated wire delay. So these complete set of combinational delay should be less than 390 picoseconds or 0.39 nanosecond that we just derived. That's the whole idea. And once we assure that this combinational delay is less than 390 picosecond, which means this section of the circuit will work on under any conditions. It seems to be a bit difficult to achieve that because it's a very long path, but we'll see how do we even take care of all these kinds of things. Basically what we do is we take all the fastest cells over here and we try to do a direct route between this particular. Let's look into those parts in the further slides. Okay, so we'll now move into the green colored logic where you have this particular flip-flop 1 clock to Q delay. You have the estimated wire delay from flip-flop 1 to logic cell 1. You have the delay of this logic cell 1. You have the estimated wire delay from 1 to buffer. You have this particular buffer delay. You have the estimated wire delay from buffer to 2, and you have the delay of 2 and the estimated wire delay from 2 to flip-flop 2. So these combinational delays, whatever we have derived just now, has to be less than 390 picoseconds or 0.39 nanosecond. That's the whole idea. That's the whole complexity. The complexity arrives at that point when we try to balance or when we try to get this particular combinational delay less than 390 picosecond, but because it really looks very hard to achieve that, but we'll see what can we do about it. Okay, next that comes under the data slew check. Next that comes under the timing analysis check is the data slew check. So data slew, what we do, we trace the data path. Okay, we trace the data path right from the IO port to the from the input port to the output port, and try to capture the transition values for each and every one of them and identify what should be the range. In this case, the data slew has been given a range. It should be greater than 20 picosecond and it should be less than 400 picosecond. Let's look into how does this range comes into picture. Okay, quickly we'll have a look. So for example, let's trace this first data path. So we have this flip-flop 1 to flip-flop 2 and it goes from D in 1 to D out 2. Okay, so we calculate the data slew at this point. So basically a signal which is sent from D in 1, it reaches flip-flop 1. It has to, while in that process, it has to charge all the capacitances which are there in the path, at least the estimated wire capacitances. It has to charge all of them and also the input capacitance of flip-flop 1. So it has to charge all of them, and then the charging waveform for it will become the slew for it. So for example, let's say this is the charging waveform. The capacitance charging waveform is this one, and the slew is this part, the part from where it goes from logic 0 to logic 1. Okay, so this is this slew part. So so we were talking about the data transition in the previous videos where we mentioned that why do we need even repeaters. So basically, if this particular slew, if this particular value of the data transition is exceeds 400 picosecond or is less than 20 picosecond, in this case if it exceeds 400 picosecond, we need something called as repeaters, because because this constraint or this condition says that anything that exceeds your 400 picosecond value, we can't guarantee what will be the how the circuit will react to it. And the reason for that is this particular flip-flops or any logic cells has been characterized for a range of transition. We have to maintain these slew values in this range so that this logic cell works as it is expected to work in a plain and simple language. Okay, so similarly we trace the logic, we send this particular signal to the next logic level and we see what is the transition value and check whether this value lies in this range. Okay, we forward this slew value or this data transition value and check whether the new slew value lies in this range, and so on. We keep on doing that unless and until we find that there are some slew values that exceeds 400 picosecond, and if it exceeds, we just add a buffer to it, or we do something about it. We'll talk about that, but we make sure that the slew, all the slew values should be between 20 picosecond and 400 picosecond. So what we'll do is, in the next video, we'll take up one of the slew value. Okay, let's say we'll take up this slew value and try to explain why do we have this range. It's in from the power terms, from the leakage and the short circuit power terms. We'll try to explain why do we have even this range. Okay, so since I'm already running out of time, let's try to take this particular transition value and try to explain the significance of having a min and a max value for the transition in the next video. Thank you.